everyone. Today we will have the last lecture, and this lecture is basically a kind of supplementary lecture in order to complete the concept what we started doing or understanding in lecture 40. So, this is lecture 41. And we will discuss the main topic would be of course same as the previous one, which is oxidation of metals and alloys. But mainly we are considering metals, pure metals, and the subtopic for today is oxide structure and oxidation mechanism. In the last lecture, we ended our discussion on the structure analysis of zinc oxide, and we saw that there could be two types of oxides, one is P type or N type, and out of P type there could be two situations. One situation could be a metal deficient oxide or oxygen excess oxide. In case of N type, either it could be metal excess oxide or oxygen deficient oxide. So, there could be two oxides, one is P type, another one is N type, and in the P type there could be two situations. One is, for example, if this is the metal oxide, it could be 1 minus delta O or 1 plus delta, and delta is a small fraction which actually is nothing but the measure of deviation from stoichiometry. Since the stoichiometry of this oxide is 1:1, but once you have these two situations, one is this, another one is this, you are actually deviating from stoichiometry. N type could be, there could be two situations. For example, again this is MO, which is N type oxide, let us say. So, then it could be either M1 plus delta O or MO1 minus delta. These two situations can be possible, and where again delta is nothing but the small fraction, which is nothing but the measure of non-stoichiometry. Now, out of that we started discussing about M 1 plus delta plus O, which is an N type, which is a N type oxide. One classic example is zinc oxide, and in this oxide we could see that zinc cation, which is the extra that is present in the oxide lattice, goes to interstitial, and because you have extra metal cation, in order to fulfill the neutrality or the charge neutrality of the oxide. So, the concept is nothing but the charge neutrality should be maintained, whether is its metal deficient or metal excess or oxygen deficient or oxygen excess, that oxide should be neutral. And in order to maintain that neutral, in case of zinc oxide we could see that there would be excess electron. So, in that situation electron would be the charge carrier, and that is what it is called N type. And interstitial zinc cation, they can exchange sites with the nearby vacant interstitial site, and then the diffusion of metal ion would take place. So, now we will first try to understand N type case, two cases, and one example for this could be zirconium oxide or niobium oxide. So, those are oxygen deficient oxide and also N type. So, let us see how the oxidation process happens in case of oxides with metal deficient with diffusion of interstitial cation. Now, we can have two situations, one is this, another one is this. Since we have understood the structure nature of zinc oxide, let us understand if the situation is like this. So, now N type with MO 1 minus delta, this situation. This is a kind of imaginary oxide, that is what we will take up for our understanding. So, we can have a kind of structure like this. So, for example, this cross is metal cation and round is circle is oxygen anion. So, if the distribution is like this, so now if I see a simplistic approach, so here we have this is oxygen anion, this is metal cation and this is the vacant oxygen cation site. So, here we have two vacant cation site. So, that means we have 4 extra positive charges. So, we have to neutralize that 4 extra positive charges. So, there will be electron generation. So, these electrons are the charge carrier. So, it becomes N type, but here you have oxygen vacancy from the normal lattice sites. So, the diffusion would be through the vacant anion sites. So, if I try to compare these two situations, one is N type where M 1 plus delta O, that situation. Another situation is N type where M O 1 minus delta, this situation. So, in this case we have, if we go back to the last part of lecture 40, you would understand that why there should be interstitial cation in this situation. So, now first case is a diffusion of M plus plus via interstitial jump. Now, in this case diffusion of oxygen ion via vacant anion sites. So, this is the difference between the diffusion of species. Now, in this case the anodic reaction happens, which is M minus 2 equal to M plus plus. It happens on M MO interface, and here, and of course, these electron goes to the other side of the interface, that means oxygen oxide interface, and there we have plus 2 E equal to O 2 minus on oxygen metal oxide interface. So, these two reactions happens, this is anodic reaction, this is cathodic reaction, they happen on the two interfaces, but here also this remains same, metal 2 electron it moves to, it goes to M plus plus, and this happens on metal metal oxide interface, whereas plus 2 electron go to 2 minus on oxygen metal oxide interface. So, there is a similarity, but in this case metal ion moves to the other end and then reacts with O2 minus. So, third is metal ion migrates to oxygen metal oxide interface and then combines with O2 minus, which becomes MO, whereas in this case oxygen ion migrates to MO interface and then combines with M plus 2 form MO. So, now here the oxide growth happens on oxygen metal oxide interface, whereas here oxide growth happens on interface. Fine. This is the two distinct scenarios we can arrive at. So, let us see how we can graphically show that. For example, in this case let us say this is my oxide layer, which is MO, and of course, this is nothing but M 1 plus delta O. So, M minus 2 E equal to M plus plus, it migrates via diffusion, since there are metal ion cation interstitial, and that interstitial can exchange position with another vacant interstitial by its side, and since there is a overall gradient of metal ion on this side. So, that is what the metal ion will try to migrate or diffuse from metal metal oxide interface to the oxygen interface, oxygen metal oxide interface. And of course, these electron will also move to the other end, where it reacts with oxygen, combines with oxygen and form oxygen 2 minus, and since this metal ion goes to this side. So, this two will combine and form metal oxide. So, the oxide growth happens on this surface. Okay. So, this is a typical mechanism what we have here, and now on the other side this is the growth interface. Now, in the case where you have oxygen deficient N type oxide. So, there you have, this is again the oxide layer, which is nothing but M 1 minus delta, this is M, this is oxygen. Now, here metal loses and then form plus plus, which stays here because we do not have any missing sites or metal or cation interstitial. Now, here we have this electron, 2 electron, this will migrate to this surface and then combine with oxygen 2 minus. This oxygen 2 minus will migrate from metal oxide oxygen interface to the metal oxide interface via vacant oxygen cation sites diffusion. So, now this oxygen will ion cation will come here and then they will combine and form a metal oxide. So, that means here the growth happens on this interface, the oxide growth happens on this interface. So, this is growth interface. This is the typical difference between the oxygen mechanism in these two situations. Both are n-types, but one case you have metal ion cation interstitial, another case you have oxygen vacant sites, oxygen cation vacant sites. Now, let us see the situation in case of p type. P type case, we have two situations. One is metal 1 minus delta oxygen and second is metal oxygen 1 plus delta. These are the two situations we can come across. Now, if I try to see their structure, so this classic example of this one is iron oxide or nickel oxide. So, which can be written as iron 1 minus delta O or nickel 1 minus delta O. So, these are the metal ion deficient oxide. So, if I see the structure, let us draw a simple model, which is, let us say this is cross is metal ion and circle is oxygen anion. So, this will be the distribution. So, now we have deficient metal ion cation. So, let us put a vacant cation, then we have so now here X plus plus minus minus. So, these are the nomenclature and now this is vacant cation site. So, now since we have two cations missing, so we have extra 4 negative charges because of this excess oxygen that is present in the lattice. Now, in order to neutralize this cation would try to leave one electron and then form X plus, since X is considered to be M plus plus plus. So, X plus is nothing but M plus plus plus, which is typically a bivalent metal cation with one electron hole. So, here also since there should be 4 such situation, so now we have 4 electron holes which are nothing but the extra positive charge in order to neutralize excess negative charge due to extra cations present in the lattice. So, for example, if it is nickel, so the structure would be nickel plus 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 So, this will be the situation what you can experience. In case of iron also you can have this typical situation. Now, here the situation is little different because we have extra, and now this particular situation can arise in case of uranium oxide, where cation is very large, anion is very small. So, now if this is my cation, that is what I have drawn little bigger size x. So, this is anion, this is anion. So, now x cation with reference to, of course, this, we are not taking the actual picture what we have in case of uranium oxide, but we are just taking hypothetical oxide with MO 1 plus delta, and this is which is nothing but anion, or, and this is M plus plus with reference to this. Now, in this case we have extra anions. So, they will be in the interstitial position. So, now let me put it in this fashion, these are interstitial. So, this is anion interstitial. Anion interstitial. So, now we see that there are 4 extra negative charges. So, that is what they will have 1 electron hole, 4 electron holes should be present. So, this X plus is nothing but M plus plus plus. So, this is basically we call it hole, fine. So, now you see both the cases, the charge is, that charge is transferred via positive hole, and diffusion would be different here. In this case, diffusion is via the cation diffusion through the vacant cation sites, but here diffusion of oxygen via interstitial oxygen diffusion or the interstitial anion diffusion. So, now if I try to see the mechanism in this situation, just the way we have done for N type. So, here it is MO with M 1 minus delta O, this is a p type with cation vacancy. So, now if I try to see 1, the diffusion is of course via vacant cation sites, and here the diffusion should be metal ion, that will be diffusing. Second part, this reaction which is anodic reaction would happen on metal metal oxide interface. Third is metal oxide, and of course, the other corresponding reaction O plus 2 E equal to O 2 minus, that would happen on oxide metal oxide interface. Now, this is the cathodic reaction, this is anodic reaction. Now, we have to see which way which species would migrate, since we have seen that this metal oxide metal cation would migrate from inner surface to the outer surface, that means metal metal oxide interface to the oxygen metal oxide interface. So, that means the combination reaction would happen on oxygen metal oxide interface. Now, you have to see how the charge would move. Now, in this case the charge movement happens via exchange mechanism, which is nothing but m plus 2 and m plus 3. So, like that it will move, or you can also make it like this, m plus 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 electron equal to m plus 2. So, like that way the charge would move. Now, this is the case for metal deficient, but for the metal oxide where metal oxygen 1 minus delta, sorry 1 plus delta, which is the p type. So, that case diffusion of O2, which is the anion, via interstitial jump, metal, this will be happening on MO sites, MO sites, this will MO side. So, these interfaces they will happen. Now, oxygen is diffusing, so the combination reaction between metal cation and oxygen anion forming MO, that would happen on MO interface, and the charge transfer movement will be via exchange mechanism. So, now if I try to see graphically what happens here, now if I see the two interfaces, this is oxygen, this is metal oxide, this is metal, of course, this is metal 1 minus delta O. Now, metal minus 2 equal to m plus plus, and here oxygen plus 2 equal to oxygen 2 minus, these two reactions are taking place. Now, metal ion should move to the other end, because we have metal cation vacancy. Diffuses out, and now we have to see the charge, how this charge is transferring from this end to this end. So, we have to see the charge transfer. Since this is metal deficient oxide, so the deficiency happens where there is a combination of metal ion and oxygen ion. So, that happens here. So, here you are generating, we are generating electron hole, or m plus 2 minus E plus 3, that is forming. So, this plus 3 is exchanged in this fashion. So, this is metal plus 2 and here metal plus 3. So, electron goes to this. So, then it becomes like this. So, So, this particular reaction is taking place. So, now here M plus 3 is coming up. So, now we are generating vacancy, this electron hole here, or we simply say that hole. So, that is coming because of this, and now whenever we have this particular reaction, then M plus 3 is moving to this end. So, and then again there is another exchange of electron. So, M plus 3 is coming here. So, finally, it comes to this interface, this M plus 3. So, M plus 3 combines with one electron, it forms M plus plus, and this electron combination is coming from this. So, this 2 electron which is being released by metal, that combines with metal plus 3 and forming metal plus plus. So, now this way metal plus plus going to metal plus 3 and leaving metal plus 3, and then again this mechanism is going on. So, finally, here metal plus 3 is combining with electron and forming metal plus 2. So, that way the mechanism of oxidation happens in case of p type oxide. Of course, in the p type oxide, of course, this when metal deficiency is there. Now, interesting part is this cation vacancy which is generated here, because it is forming non-stoichiometric oxide, this vacancy is migrating through from this end to the other end. So, this vacancy movement is this way and metal ion movement is this way. So, the vacancies are coming, this metal sites, cation sites which are vacant, those coming on the other end gradually. Now, if those vacancies, for example, number of vacancies they combine each other, so that time there could be possibility of pore generation. So, let us say this is a pore which generates due to combination of migrating vacancy. Fine. So, there could be porosity formation on the metal oxide interface. So, this is the mechanism what could be possible in p type. Now, let us not continue any further from this. There is a great effect of this metal oxide structure, and that can decide how do we alloy them, so that we can introduce resistance to oxidation. For example, if we take N type and for example, zinc oxide, if we add a kind of metallic ion which has lower vacancy than the metal cation present in the usual lattice, then that would reduce the concentration of interstitial and also decreases the excess electrons. So, now if it should be lower vacancy, and now if that lower valency metallic ions, for example, lithium ion, if we impregnate in zinc oxide, then it reduces the zinc oxide cationic sites, these interstitial sites. So, once we reduce the zinc cation sites in the interstitial position, then of course, there will be reduction in oxidation rate, because the growth will be because the zinc cation will no more diffuse as faster as possible in the situation where there were large number of zinc plus interstitial sites. So, that would reduce the oxidation rate, but again if we add aluminum which has higher valency +3 compared to zinc which is +2, that case again zinc cationic sites, this zinc ion concentration in the interstitial position would increase, and that would again lead to increase in the oxidation rates. Similarly, if we consider p type oxides, let us say metal deficient oxide, nickel oxide or iron oxide, there if we add lower valency cations which is like a doping, then the concentration of cation vacancy would decrease and increase the electron holes. And of course, because the concentration of cation vacancies is reducing, and that would lead to decrease in diffusion rate of metal cation, and hence oxidation rate would decrease. But it happens just reverse if we just dope a metal cation with a higher valency than the iron, let us say. So, there for example, chromium, then chromium has got +3, whereas iron has got, nickel has got +2. So, that time metal cation sites, vacant sites would increase, and of course, that would decrease the electron hole concentration. So, since we are increasing the metal cation sites, the metal cation vacancy sites, so that would increase the rate at which the metal cation will move from metal oxide interface to the oxygen metal oxide interface. So, oxidation rate would increase. Now, interestingly, this chromium when we add it at a very small content to nickel oxide or iron, the oxidation rate increases, but if we have extra chromium, then that chromium forms chromium oxide, and then it will protect the metal part from oxidation. So, but we are not getting into the protection part or the effect of alloying on the oxidation rate. So, because that will be taken up in the next stage of the next corrosion course, which will be corrosion part 3. Now, if we try to see what we have taken up in this particular course, we have started with corrosion and we have analyzed different corrosion phenomena or corrosion events with the help of mixed potential theory, and this mixed potential theory also comes in cathodic and anodic protection, and that is what we have also considered cathodic and anodic protection and analyzed it from the mixed potential theory. And then gradually we moved to oxidation, and in the oxidation we understood we tried to understand thermodynamics and kinetics of oxidation and also the mechanism of oxidation. However, we have to now get to the protection part. Now, in the corrosion part 3, we will be taking up protection of metals and alloys. In case of corrosion, there could be protection due to alloying, there could be protection due to microstructural change, there could be protection due to working condition, and then there could be protection due to environmental change or going for coatings, going for inhibitors. So, those are the factors will be taken up in corrosion part 3, and from the oxidation side we will take up effect of alloying. That means, once we go for alloying, that means we are talking about the oxidation of alloys, how it changes, just like the what explanation, that little bit of hint has been given that if we add or dope elements with different valencies in a metal oxide, that would lead to change in the oxidation rate. Either it can reduce or increase the oxidation rate, and then there could be coatings, for example, stellite coatings. There could be boron oxide coating. Those coatings can also help in reducing oxidation rate of metals and alloys. So, for the time being, we will end here, and we will learn more in the next level of course, which is the corrosion part 3. So, till then, thank you very much.